Hello guys, so how are you? And today we are gonna discuss this paper which is known as UCF Uncovering Common Features for Generalizable Deepfake Detection. And the funny thing is that this paper is called UCF and UCF is my own school. So yeah, that's a funny story here. And let's get to this paper today. And the reason I'm covering is because this paper was is gonna be presented in one of the research talks which I will give in one of the interviews for one of the companies which I am interviewing for, specifically for for Reality Defender, which is a antivirus company. But anyways, I thought that it would be cool to make this video and see like how well we can go about this. So okay, so let's get to it. So this paper actually talks about deepfake detection and what is deepfake detection. So as you know that right now Gen AI is becoming like a really big deal, and all these generative models are actually creating like really good images, and it is getting really difficult to know that what is real and what is fake. And it is a cause for concern for a lot of people, because then they don't know like whether they are interacting with anything which is actually AI generated, or whether it is something which the machine, whether it's a real human being or not. So from a security standpoint, deepfake detection is a really good problem to solve. And as such, like it's a the technical formulation of this problem is pretty easy. So it says that, so what deepfake detection means is that you have two images, and one of the image, so you're given two images or you are just given one image, and it is either AI generated or it's generated from real world. Like it is an image which has been taken from real world, and you need to be able to distinguish between these two. So this is a real image and this is a fake image. And if you are able to distinguish between these, then you are doing a good job. So in this case, it is a basically a classification problem. So if you have like any image, it can either be real or it can either be fake. So it can belong to only one of the two classes, real or fake, and that's why it is known as a binary classification problem. So now on surface, like this is a pretty easy problem, right? Because it's just a normal type of classification problem, and we know that neural networks have done a pretty good job in doing classification. And in fact, like if you look at classes of neural net like LXNet, you know that they're doing pretty good job. And even like transformers these days, they are able to get around 90% accuracy on ImageNet for classification among all 1,000 classes. So then this should not be a big deal, right? Because you can just plug in a neural network and then have it do this job, like just train it on a data set of real and fake, and it should work, right? However, it turns out that this is not that easy, and it is challenging due to several reasons. And one of the reasons is because AI is basically like gotten so good, and the images it generates are pretty similar to the real images. So it has gotten like pretty good. And if we can't distinguish, then how can a network distinguish between these images by just looking at them? So if as humans, like if it is getting difficult for us, then it should be getting difficult for networks also. And turns out that so let's look at like how could you go about solving this problem. Okay, so the first thing is that if you look at the direct classification, so there is like one type of approach possible, in which what you do is that you just take an input image. And so the naive way like which you will go about solving this problem is that you will take an input image, and then let me zoom on this figure a little bit. Okay, so the way like you could go about solving this problem is that uh, you could take like an image, and then you could have a neural network, which is in this case is a CNN, and you could just compute like a feature vector from it and then classify the resultant image as real or fake. So this is like the first solution which comes to our mind. Okay, however, like there is some problem with this, because what we can, so if you just do like this sort of direct classification on this task, it does not work quite well. The reason is because the images which are generated by AI and the images which are generated by a normal from real world, like the images which are taken from real world, they are pretty similar. So just by doing this sort of real and fake classification, it doesn't work that well. Okay, so now what is the second thing which you can do to solve this problem. The second thing is that you can so the second thing is that you can learn like two kinds of features, right? So the idea is that if you have like an input image, so generally this input image has like two types of features. One is a content feature and one is a forgery feature. So the idea is that the content feature is basically the feature which only talks about what is actually present in an image. So in this case, we can see like a photo of a girl. So in this case, the content feature actually means that that you capture the semantics of a girl, okay? And then there are like, if you decouple like some features which are corresponding to forgery. So for example, let's say this girl was like forged and it was generated by a model, so there will be some features which are corresponding to the model which actually faked this and which actually applied the forgery to the girl, right? So in that case, those kind of features are actually known as forgery features. So now what happens is that you can, if you manage to like disentangle these two, so once you feed like your image into the network and then whatever you predict, in that case, like you get content feature and forgery feature. If you are somehow able to disentangle these two, then technically you can use like these forgery features to do some sort of task like classification, which is real or fake. And the hope is that it will perform better than this baseline, which is in the part one of this figure, right? However, like the problem is that however like the problem is so the problem is basically as follows. So let's say that this image of the girl was actually for this image of the girl was like, so during training, let's say you have like images and these all are fake images, okay? And your training set only contains like forgery sources from different models like M1, M2, M3, M4. So if you like decouple, if you try to like if you try to like learn these forgery features in such a way, then what will happen is that your network will only learn the forgery features for the your network will only learn forgery features which are corresponding to different models which are seen during training. So in case like in your training data you generated fake images by using different models like M1, M2, M3, M4. So in this case, the model, when you just try to disentangle these forgery features will only contain information corresponding to M1, M2, M3, M4, and it is like very difficult. So your network is essentially overfitting to the forgery features belonging to the models in your training. So it is not able to. So now in inference, during inference, if you give like if you have another image which is with another fake image which has been generated by another model, let's say from a model M5, and if you try to feed that to the network, then network will not be able to understand it, because in this case the forgery feature from M5 it has never seen before. So in this case, as you can see, if you just try to like disentangle only content and forgery specific features, then the forgery features you obtained, they are actually only corresponding to the models which have been seen during the testing, during the training. And if you during inference, like if you have any other fake image which was generated by some other model, in our case M5, then it gets really difficult to do this job. So this is like, so these are like the two type of contemporary approaches which have been done in this field. So one is like you do naive classification, which the authors call direct classification, and the other way is that you are trying to actually disentangle the content features from the forgery features. But in this case, what happens is that the forgery features are actually overfit to only the models which actually generated the fake images during training. So yeah, so if during inference you get any other model which acts like a sort of fake generator, then your model is not able to distinguish between M1, M2, M3, is not able to distinguish between M5 and all these four, because it has never seen like M5 models forgeries during training. Okay, so now the point is that uh, this is like a limitation, and what is like the key problem you want to solve. So the key problem you want to solve is that you are given like a bunch of fake images during training, and they come from like a set of, and these fake images come from like a set of models M1, M2, and so on till Mn. And during inference, like, you can be given any of the fake image or a real image, and these fake images could be generated by some model which you don't even know about. It can be generated by some other AI which you don't even know about, and that can be like a model n plus 1, a model n plus 2. So you need to be able to understand that the forgery came from like different sort of models, even though like you never saw images generated by these models during the training. So, how do you go about solving this problem? And this is like the core idea about this paper, that how do you actually learn, how do you actually learn, like, how do you learn the common forgery features for the purpose of generalizable deepfake detection? So, what the authors say is that when you are given an input image, there are actually three kind of features which you can disentangle from it. The first feature is a content vector, which is, in this case, it is like all the semantics of the girl, okay? And then there are like some features which correspond to the specific type of forgery. So for example, let's say this fake image was actually generated by a model M1. Okay, so in this case, you will actually you will disentangle like some forgery feature which they call as specific forgery feature, and that will actually give you that these features will actually detect that this model was like this image was generated by a model M1. And similarly, like in the content, similarly, what you do is, the key part what they do is that they're trying to learn these common forgery features. And what these common forgery features are doing is, they're trying to learn these common forgery features. And what these common forgery features mean is basically, okay, so what these common forgery features mean is that these features are actually corresponding. So like, if you give it any fake image generated by any model, then these are the sort of features which we care about. So the network will start predicting these sort of common features which are common to all the forgeries, whether you have seen them or not, like all the specific type of forgeries. And if you manage to decouple these sort of common features from your network, then you can essentially use them for real or fake detection. So, so I would like to make, so that is the whole point of this paper. And let's look at it in more detail. So, so basically, what problem the authors are saying here is that existing detectors generally perform well when training and testing data are created using the same forgery techniques, which is what I am saying, that this method will only work well if your fake images which were generated during training came from like model M1, M2, Mn, and during testing also they came from the same model which is M1, M2, and Mn. However, the problem is that in the real world, what happens is that your images are created by unknown procedures which we don't know about earlier. And that is like a key problem, right? So how do you identify such generalizable features? And what they're saying is that generally what happens is that there are existing methods like face X-ray, and what they do is that they assume the presence of a blending region in the forged image, which could potentially curtail the effectiveness of the approach. So So what the authors say is that there are some methods which are relying on deepfake detection, and what they are essentially assuming is that, so you have an image which is real, and when it was actually forged, what will happen is that it will have like this sort of bleeding artifact, some edges which are which are gonna be detected. And if you're able to detect these edges, then it means that it is fake. But the point is that with the advances in diffusion model, it is getting really hard, and they generally don't exhibit this sort of bleeding artifacts. So what the authors are saying here is that there are so the problem of deepfake detection can be solved by actually decoupling like a image into two type of features, which is the content feature and which is the forgery feature, okay, which they refer to as fingerprint. And the key point is that how do you actually try to disentangle, this type of content and forgery features together from the model. And that is like one of the key questions which we are concerned with right now. So how to disentangle content and forgery features together. And similarly, so that's the whole point. So one of the key contributions of the authors in this paper is that when they are disentangling this forgery feature, they are actually disentangling two types of features from this. So one feature is actually known as forgery specific feature, and one feature is actually known as the common feature, which is the features which are common to all the forgeries. And let us look at how they are actually solving this type of work. Okay. And they have like some technique through which like they are able to disentangle the common and specific forgery features from the content features. So the one line takeaway of this is that you are given an image and somehow the authors are disentangling like the content, the forgery specific feature and common feature. So these two are the fingerprint, and this one is the content feature which you are concerned about. Okay, so this is a cool plot which the authors made, and what this is showing is that if you take like a sort of exception architecture, which is a type of CNN architecture, and you train this architecture just to predict like real or fake images, then what happens is that, and then if you, for the testing set, then if you are trying to like predict the features and you perform a TSNE clustering on top of them, what will happen is that you will observe that these features are actually clustered according to the different kind of methods which were used during the forgery. So let's say your training set consisted of five kind of things. One is real images, and one is that the data, which is four types of models were used to generate like the four fake images, and they were generated to use four kind of fake images. So then if you plot the TSNE, then what you can see is there are actually four regions corresponding to different fake methods, and there is one region which is corresponding to the real method. So during inference, if you are given the forgeries from the same models like deepfake, face-to-face, face swap, and neural texture, it will be able to detect it well. But if you are given like if you're given like a forgery from some model which was never seen during training, whose generated images were never seen during training, then the network has no idea about where the forgery feature will lie. So here it is only exhibiting the quality to distinguish between the forgeries of four models, and that's not good, because if you have a fifth model, then it doesn't know where to place them. It might end up placing them here, but that's wrong, right? Because that might be some fake sample, and there might be a separate subspace which is possible for a fifth method, but it has never learned that because it never saw the features from that model during training. So this is like a key problem, which is that how do you build something which is actually method specific textures, and how do you build the ability to generalize to other unseen forgeries during the during the learning process. Okay, so now let's move on to the next part, which is the method. Okay, let's look at their architecture and what they are actually doing here. So what they are saying is that they have like this model which takes like, so their architecture is like a sorry okay So their architecture is like consisting of two parts. One is an encoder and one is a decoder. So first let us try to understand what the encoder contains. Okay, so in encoder is actually processing like a pair of images at a same time. So the encoder is a pairwise architecture, like a Siamese sort of network, and it looks at like these two images. So for now, so the encoder is processing like two images at a time, one real and one fake. So here this is real and this is fake. And what happens is that, let's say that the image through let's say that the fake image passes through the encoder, and what they are doing is actually they are decoupling. They are actually uh, they are actually decoupling two kind of features. One is a content feature and one is a fake feature. Okay, so this is actually the content and this is the fingerprint. Now the key point is that, so here what they say is that encoder is basically a network which processes a pair of images, and the encoder comprises of a content encoder EC and a fingerprint encoder EF, extracting the content and forgery features. So the key point is that if you look at their encoder can be partitioned into two parts. One is a content for one is a content encoder and one is a feature encoder. One is like a fingerprint encoder, and once you feed your image to it, so let's say you just fed one image, it will predict like this. It will predict like this content feature C naught, and it will predict these two fake features, which is F1 and F2, which are like the fingerprint features in our case. Okay, and so that is like the architecture of the encoder. Okay, so now let's look at like what is the decoder. So the decoder is like pretty important design which we have never seen earlier before. So let us imagine. So I would like to take a detour here and try to explain like how and try to take a detour here and try to explain concepts from neural style transfer. Okay, so concepts from neural style transfer. So what happens in neural style transfer is that you are given like a content image, and generally what you are given is another style image, and you are trying to create like a new image which contains like the content and style together. Okay, and so for example, there is some image and the style image comes from a painting of Van Gogh, and you want to generate a new image which is actually containing the original image along painted in the style of Van Gogh. So the point is that you want to build a network which can do this job for any given content and style. Okay, so they and it should be like able to generalize to new styles, and there has already been like a work which has happened which is called adaptive instance normalization. What it does is that it takes like the content features as input, and then it actually removes like the content information from the it actually removes like the content information from the image by calculating like the mu and the sigma, and it actually normalizes it. So once you actually remove the information, the resultant vector only contains, so it is like essentially normalized in the range of like a standard Gaussian distribution. And then what happens is that the only information of the content which remains is in the relative magnitudes of these numbers. Okay, and then what you do is that you feed like your style images through these layers, and you try to like actually compute like what is like the variance of the style image and what's the mean of the style image, and then you try to add them together. So in this case what happens is that you take your content feature and then you destroy some sort of content information from it, and then you are applying like some style computed statistics from it, so that whatever resultant features you get are actually containing the style applied onto the top of content. And it has been found like once you do this sort of normalization, then what happens is that the network is able to generalize to various styles and various contents. So it is able to generalize even to like several style images which were never seen during training. And that is the key point which these authors are taking in the context of forgery detection, where they are just swapping this style with the forgery features. So if you look here in a closer detail, what is happening here is basically as follows. So you are having like a content fingerprint. So your decoder is basically so your decoder is basically taking as input the content. Your decoder is actually taking, let me just go there. Okay, so a decoder is taking like the content image as input, and it is also taking like these two fingerprints as input. Okay, so these are like the fingerprints. Okay, sorry. Okay, so I am back. So in this case, if you look at the decoder, let's reset this and look at the decoder in more detail. So what the decoder is actually doing is that it's saying that you have like a content feature of an image and you have like the fingerprint forgery feature which you have decoupled. And what you have done is basically that you are taking these two. So you have two branches in this decoder and you're taking like the content here and you're feeding it to an adaptive instance normalization layer. Okay, and in this adaptive instance normalization layer you are essentially taking like the forgery features and you're appending them to the adaptive instance normalization layer. So basically you're trying to remove like the content information and you're trying to apply like the forgery information through this adaptive instance normalization layer. And then what you're doing is that you are upsampling it through a con block. So you're trying to regenerate the image which is actually given, and then you do this job for like a couple of blocks in this case, which is like a adaptive instance normalization block along with like convolutional upsampling, and finally finally you are able to regenerate a image. So here what dc0 f0 means is that you're given a content image c0 and it has a forgery specific feature f0, and you're able to generate an image which is like the combination of like the content and the forgery together. Okay, so this is basically what they call as their decoder. So in their decoder, they have what they're saying is that the architecture of our decoder D involves combining the fingerprint and content through adaptive instance normalization layers, which are then processed through multiple convolutional blocks. So here, if as you can see, there are two convolutional blocks along with the upsampling layer indicated by con block. So the con block is the upsampling layer, and they're using like the adaptive instance normalization twice. So that's the whole point here, and that's how like they're able to build this kind of decoder. Okay, so now this is like their method, and let's look at like what's the key point and how they are able to actually train this whole thing. So now the key point, like the key questions which remain unanswered, is basically how are they able to get like how are they able to like get this content feature c0, and how are they able to get like these fingerprint features. And this fingerprint feature is actually partitioned into two parts. One is like the forgery specific feature, and one is like the common feature, which is features which are common to all the forgeries together. Okay, okay, so let's look at it in the next slide. Okay, so the way like generally, so the way they are actually training their network is they have something which they call a multitask classification loss, and the idea is pretty simple. So let's say that they have their network, and their network is actually predicting like a uh, the network is predicting like a common feature, which is like some features which are common to all the forgeries which could happen, and some is there is like a feature which is like specific to a particular forgery. Okay, so in this case, like for example, if you're given an image and you know that a model m1 was the one which actually generated that fake image, then how will you supervise this network? So you can actually, so this common feature is a feature which is not dependent on any model, right? So you can say that, but you know that whether the given image is real or fake. So in that case, what you can do is you can just get like a label 0 or 1, and you can supervise this whole thing by a standard cross entropy loss. Okay, and that is what like the original equation is saying, that you have like, so yi is a label which says whether the given image is real or fake, and you can easily supervise this branch of the network by using that type of cross entropy loss. Okay, now also let's look at the other part here, which is that which is basically the forgery specific head. So what it says is that so let's say that during the training you actually had like a lot of fake data, and it was generated by models m1, m2, m3, m4, and so on. So what you can do is like here you can pose a multi-class you can propose a multi-class classification problem, and what it says is that the network consists of like several neurons, and it can either belong to like it has either been generated by model M1, M2, M3, or M4, and you can supervise this by a standard cross entropy loss. So there is nothing new which is happening here, and you can in this way like you can learn the features which are common to all the which are common to like which are specific to several models which generated the data. Okay, so this is like the whole point. So in this case, like for example, uh, when you're given the model M1 which generated this fake image, you can actually predict that the model M1 generated that, and you can apply like a cross entropy loss here. So this is like the feature which is specific to a particular model. Okay, now what is like the reconstruction loss? So the reconstruction loss is pretty amazing, and let's look at it in the following way. So what they are saying is that let's say that your network has so let's say that your network has managed to so let's look at this image. Okay, so in this image your network has managed to decouple like the content and the forgery features together. So if you take it like your decoder, so if let's say we are talking about this image which is the fake image, and you have right now predicted like this content feature for it, and you have also predicted the forgery feature for it. So if you feed like this content feature and the forgery feature for this image, you should be able to reconstruct the image back, which in your case is basically the fake image. And similarly, if you do this job for the real image, then you should be able to actually you should be able to reconstruct the real image as well. So if this is like so this was like fake forgery, and let's say you have real content and then you have fingerprint for real content, then you should be able to regenerate the real content as well. So that's the key part, that you take these features, you regenerate the input image back. And similarly, you take these features and you regenerate the input image back again. So let's look at like where it is happening. Okay, so here if you say that they have like two types of reconstruction, one is basically the self reconstruction. So here you can say that they are taking like the final output x0, which is like the input which they fed. So they are saying that when the decoder sees like the content feature and the fingerprint feature, it should predict the same image as which was fed in. And similarly, they are doing this for like the fake image, and they're doing this for the real image as well. Okay, so that's the whole idea. And similarly, like what they are saying is that you can do this job in an opposite direction. And what this means is that what this means is, for this you can go to the earlier slide. So here let's say you have so let's say that let me clear this. Okay, so let's say that you are given like a fake image, and then you are given like, so let's say you have this content, and then instead of taking like these features, you actually take these features. Okay, so now in this case the point is that this fingerprint is corresponding to a real fingerprint because it is coming from a real image, and then this is just the content of the fake image. Okay, so if you try to combine these two, then nothing should happen, right? You should be, if you try to combine these two, you should be able to generate the same fake image which you send in. So if you take like the features, so if you're trying to take like the content from the fake image, and then you take like the fingerprint from the real image, and you try to combine these two, you should be able to get back the same image which you started with. So that's the whole point. Similarly, what they are doing is they are doing this in the opposite direction, which is that if you take like the content of the real image and you try to combine the signature of the fake image, then nothing should happen because the network knows that it's a real image. And so then nothing should happen because the network knows that it is a real image. So even if you combine like the fake fingerprint in it, then nothing should happen, right? So this is something which they call as this is something which the authors call as cross reconstruction loss. And that is here what you can see is that, so here you can see that they take like the content of the original image, and then similarly they're taking like the fingerprint of the fake of the real image, and then they are trying to like regenerate the same thing, and nothing should happen, and they are trying to learn this type of invariance in their network. So this is like the reconstruction loss. So this is like self reconstruction loss, and this is like cross reconstruction loss, where like they're learning like that if you have like some real image, you have its content, and if you add like any fake signature to it, then nothing should happen because it is actually a real image. So that's what they are trying to enforce here. And this is something which they call as reconstruction loss. And then the another thing which they are proposing in their network is basically something known as the contrastive regularization loss. So let's take a closer look at what this means, and you should be able to understand it really well. So what they are saying is that they enforce, so they have like some positives and they are having some negatives. So what they are, and they have like a given image which they are considering. So in this case you have like a anchor image A. So they have like three images, one positive, one negative, and one anchor image, and they want the positive image, they want like the positive image to be closer to the, they want the anchor image to be closer, so that you have the anchor and you have the positive, so you want these two to be close, and then you want like the negative image to be really far away from this. Okay, so that's the whole point. And in this case they say that the features are coming from, so you can have like features xa corresponds to features of a genuine image, and xp would represent common attributes of another real image, and xn signifying the attributes of a manipulated image. So what they're saying is that if you have like a real image, so if you have like a real image and you extracted like its features, and then you have another image which was real and you extracted its features, so these two features should be closer to each other, and similarly the features like should be, for fake image, should be far away from this. So let's look precisely at what they are trying to, let's look precisely at the features which they are trying to understand here. So here they are saying that XA corresponds to common features of a genuine image. So they are saying that XA corresponds to common features of a genuine image, while XP corresponds to common attributes of another real image. Okay, so what do we mean by common attributes here? So if you see here, what they are saying is that the fingerprint consists of two parts. One is common fingerprint, one is like fingerprint which is common to all the forgeries, and one is a fingerprint which is like common to, one is a fingerprint which is common to like specific. So this is, one is common feature and one is a forgery specific feature, right? So the key point is that if you take like a lot of data which is real, then all of its common features should be close to each other. And if you take like the data which is like fake, all of its data, all of like the fake data features should be close to each other, right? So they apply this constraint to the common features. So what do they, so that's what they are saying. So let's say you have image 1 which is real, then you have image 2 which is real, and you have image 3 which is fake. Then what you can do is you can compute like the common features of these three, FC1, FC2, FC3. So FC1 and FC2 should be close, and FC1 and FC3 should be far. So that is what like this whole thing means, and it makes sense, right? Because you're trying to like generate like these sort of common features. So the features like which are for all the real images should be close, and features for all the fake images should be close, and the features for all real and fake images should be far apart. So this is the constraint which they are imposing, and they call this constraint as contrastive regularization loss, which was like, which is like the type of thing which they are trying to do here. Okay, And so now the key so this is like for different kind of images, and they are also like getting, they are also applying this loss for specific features. So what they're saying is that for the specific imager, we compute the loss between images of the same forgery to encourage the model to learn method specific textures for each forgery. So what does that mean? Okay, so let's look at this from another perspective. So let's say that you have two models. Let's say you have three images, and these three images are generated. So let's say there is image 1, there is image 2, there is image 3. So let's say image 1 and image 2 are generated by the same model M1, and then you have image 3 which is generated by a model M2. Okay, so what you are trying to do is that if you are actually taking like the specific features from this, the forgery specific feature fs1, forgery specific feature fs2, forgery specific feature fs3. So in this case fs1 and fs2 should be close to each other because they correspond to forgery specific features from the same model, which is m1, and similarly fs1 should be far away, it should be far away from another model which is like fs3, because they correspond to different, they correspond to like different models. Okay, so here this was generated by m1 and this was generated by m3. So you can imagine that this kind of loss is actually applied to both real images, as well as is applied to like both common features, as well as it is applied to both, it is also applied to like specific features. So that is like the good thing which is happening here. Okay, now let me move further and try to so these are like all the constraints which they have on their network, and the only way like which they could apply this. So if you see here, like if you, the only way like they could apply this loss was if you had one real image and then several fake images, and that is like the justification of why they are actually applying their network on a pair of images. Okay, so that is why like in figure 1 they are operating on a fake image and they're operating on a real image together. Okay, so what does their inference look like? During inference, what they do is that they take an image and they're on, and they take like the encoder, and they get like all the three features, which is like the content feature, which is forgery specific feature, and one is like the common feature, which is like common features to all the forgeries. So this FIC here means the common features of all the forgeries together. So they only take like this common feature and and then they decode it and through their like classification head and classify it as fake or real. So they are actually not doing anything with the content feature and forgery specific feature during the inference. They're only taking a look at the common feature which they are using to classify. Okay, so now that this is clear, let's look at, let's try to look at their results, what they're doing. Okay, so what they're doing is that they're showing the results. So they're showing, so there is a data set called FF plus. So FF plus is like a data set which contains like more than 1.8 million forged images from 1000 pristine videos. So they have 1000 videos from which they extract the frames and they are actually forging them, and these images are actually forged using like different kind of methods like DF, face to face, face swap, and neural texture. And what they're doing is they are training their network on this FF plus, and they're training it on a high quality version of the data, which is like very high quality, so high resolution images. And then they're trying to actually, once they have trained their model, they're actually trying to test it on these three data sets, which is DFDC, Celeb DF, and DFT. Okay, so let's look at, like what their results are. So here what they're showing is that, so So they are like basically, so when they're training, they are training using all the images in the FF dataset, and then they are removing like the images which were generated by DF, F2F, and FS and NT. So these are like the four methods, four models which were used to like generate different kind of fake images. And what they're doing is that they're training like on these one, two, three, four, five. They're training on these five different kind of setting, and for each setting they are evaluating like zero shot scores on these three models, on these three data sets. And as you can see, their results are like among the best here, which is a pretty cool thing. And that's what like, so they are like getting consistently getting pretty good results on like the face classification task, on a deepfake classification task, which is like really impressive. And this paper like right now has, it was, I think it was published like 2 years ago, and right now it has around 200 citations, which is like really impressive for this kind of work. And hopefully like it is also effect, it's also like motivating other future directions in this type of work. Okay, so now let's look further. So this all is good, but let's look at their ablations, which are like really good. Okay, so in their ablations, what they are showing is that what they're showing is that there is a normal called exception architecture, which was only trained by using like, so they, you have like exception and you have like an input image, and you just train a classifier on top to call it like a real or fake. So if you just look at like this type of exception architecture, then it only gets like 98.6. Okay, and then a better way is to actually do like a meta way, and then once you try to like disentangle like the content and forgery feature together, once you try to like disentangle the content and forgery feature together, what you obtain is basically 99.5. So 99.5 here is better than 98.6. So what they're saying is that rather than just training this kind of model, what you can do is that you can train it in a disentangled way, where you are trying to learn like the content feature and the fingerprint feature, which is something there, which is like good, and that actually gives you some improvement. And then they have like this thing called M, and M is basically the multitask learning module. So what does M mean? So let's go back to their paper and see what was the multitask module. Okay, so this was the multitask module. Okay, so what the multitask module means in their ablation is basically that while you are like learning these features, they are also trying to predict like which specific method actually generated that feature, right? So whether it was generated by model 1, model 2, model 3, model 4, or something like that. And that kind of additional constraint is actually improving the performance almost. So it's not improving in FF dataset, but it's actually improve on celeb DF datasets. It's actually lending itself to like around 2% improvement. And then the final thing is this contrastive learning module, which they had. And this is like the final contrastive learning module, which actually gave them like the best performance for their architecture. So this is like really good. And now some other ablations which they show are also good. So one ablation is that so in the decoder, so you remember that in the decoder there was like, in the decoder like they were actually using like, they were having content feature, and they were having actually the feature from the fingerprint feature, and they were actually using adaptive instance normalization layer to combine those two. So one simple way which they could combine the feature was by simple addition of the features, but that only gave them 99.5. But if you actually try to use like instance adaptive ADA type of layers, then you get like better features, which is 99.6. And similarly, the other ablation they did is that they tried to like predict, so they're actually trying to like predict like specific forgery feature and common forgery. So what they're saying is that so if you look, so the fingerprint they were predicting, they were trying to predict like some common features, and they were also trying to predict some forgery specific features. So what they're saying is that if you use like the common forgery features for classification, that actually performs really well as compared to using only the specific forgery features. And that's like somehow true, right? So during inference, like let's say your model only looked at M1, M2, M3 features, then you gave it like which are used to generate like the fake data, and you only gave like another model M4 which was used to like generate the fake data during inference, then the model will not be able to understand this, right? The model will not be able to understand the information about M4 because it has never seen M4 before training. So forgery specific feature only contains information of M1, M2, M3, and since it doesn't contain information about M4, it will not be able to capture that. So that's why, like, if you look at like the common forgery feature, the common forgery feature is the correct one to make inference from, and they actually validated that insight by doing this. Okay, and then the last ablation which they have is also pretty interesting. So what they're saying is that their method results are not only due to exception. So when you have a normal exception, which is like a normal real fake, which is like a normal linear probe, and if you apply like their method, which is the disentangling framework, along with like multitask learning and contrastive regularization, then you get like a very good performance. But if you also take like another backbone like connext and you apply their method on top of connext, then you see a lot of improvement from 77 to 84, which is also like really impressive, which is I think around 7% improvement. So yeah, so what they're saying is that this approach of actually taking like the input image and then decoupling into content and fingerprint, and decoupling the fingerprint further into forgery specific feature and then common features, is something which carries over across like different backbones, and this method like generalizes and it does not depend on the backbone quality. So whatever backbone you give it, it will actually improve the performance, and that's like really impressive. Okay, so that's all which is to their paper. And now let's so here like here they are just saying that here what they are doing is like they are just trying to show like the different kind of images which their models can generate. So like let's say you fed it like one fake image and one real image, and then you can generate using the decoder, which is the conditional decoder, you can actually generate like four kind of images, which is like when you have content of this and style of this, similarly content of this and style, when you have content from here, style from here, or content from here, style from here, and then you can do that for this image also. So there are four possible combinations possible, and you can see like the image is essentially, these are like the four kind of images which their model is able to generate. So yeah, so this was like what the authors of this paper have really done. And from what I know that this paper, so there is like a GitHub repo, and this detector is also known as a UCF detector, and it's like very funny, and but it's like a really good detector, and the code is also simple, around 350 lines. So you can actually go and try it out in that GitHub repo, which I will link below this video. Now, let's look at their conclusion. They are saying that they should be able to capture the generalizable features across different kind of forgeries, and they hope that their framework represents a promising step towards the development of more generalizable deepfake detectors. Okay, so now that this is complete, let us also talk a little bit about what are the limitations of their work. So there are several limitations about this work which stood out to me. So the first limitation about this work is basically that all the experiments are done using images only. So what about deepfake videos? And it is like not trivial to see like how will their method work on deepfake videos, because there is like this notion of temporal direction, and how do you like add like temporal continuity, or like how do you build like features So if you have like a deepfake video and it is also like very temporally consistent, then how can you actually build something which is able to differentiate between like a deepfake video or a real video? So how do you like construct some sort of like representations which are able to capture this temporal difference? And that remains like a very interesting thing. Similarly, the other part is that the biggest problem in their network is that in the training set they are assuming that, so in the training set, like if you know, if the training set consists of real and fake data, so what they're assuming is that for each of the fake image, you know which model generated it. So, but in real world, like sometimes when you're trying to generate the data or like someone gives the fake data to you, sometimes it might not be possible to know which method generated that fake data. And in that case, like their method will not be able to work that well. So that is like another limitation of their work. And let me think about some other let me think oh yeah, the third limitation which I feel in their paper is basically that all they talk about is basically cans and cnnns. And although it's not a limitation, but like since then a lot of advances have happened in diffusion architectures and similarly in transformers, and it would be interesting to see like how such insights actually transfer to these large data sets, to these large models, and these other kind of architectures. Okay, and there might be a lot of future work which stems from it, but I'm not sure because I haven't looked at the future work yet. But the next set of videos which I will construct will actually look at the future work which is happening and try to like decode it, and also try to get more ideas about what is recent in the field of deepfake detection. Okay, so before I wrap up, or what I want to say is that this is not a video I would make generally because it seems like an application based paper which has like a lot of positive consequences for the society. And I hope like the other videos I make keep focusing on neuroscience and biological perspective of the things and a deeper understanding of how neural networks function. So yeah, and one of the reasons I'm still making these videos is because I'm jobless. So like neat code, I just thought that okay, it would be cool to make these videos and pass on the learning to some other people who have the patience to listen to me. Okay, thanks for all. And if you like this, please go and hit subscribe below. And I would love to hear more about, if you have like any suggestions of the papers I should cover, I will cover them from the next time. Thank you.